Welcome back to Not Enough Projects. Today we're back on this 91 Camaro. Last time we were working on this, we got the brakes all squared away. This time we need to figure out why the buzzer is constantly on and why the parking lights are constantly on. So I'm guessing the buzzer is on because the park lights are on. I'm just letting you know that the lights are on so you don't leave it on and drain the battery. So you can see the issue is you can't push the switch all the way in to turn it off all the way. Now this is a pretty common problem from what I understand. There is a little plastic nut kind of thing that holds the switch in place so that the rod can move in and out. Probably that nut is just broken. So what we're going to do is we're going to pull the tail light fuse so that we can get rid of this buzzing, and then we're going to have to pull the dash out so that we can get to our light switch. So we need to start under here. We need to take out these two bolts here and here. So these bolts are both 10 millimeter. We've got another one here. Okay, we don't need to pull it all the way out. It'll just hang there, which is fine. So now we need to take these bolts out that hold the bezel on. These bolts are 7 millimeter. There's a clip, I believe, back here. So we're gonna need to push up on this clip and pull out and do the same over here. Now this bezel should come out. We're gonna have to unplug both this fog light connector. We'll have to do the same thing for the defrost connector. Okay, so we disconnected the fog light connector here. The cigarette lighter here, you just pull those away and pull out. And the defrost button, you just push these out and pull out. So now we need to remove the 7 millimeter bolts holding the gauge cluster in. And then finally, we'll be able to get at our light switch. You can see here is the broken plastic nut retainer thing I was talking about. And that's why it wasn't going all the way back. Oh, we've got two more screws up here. Alright, I got the rod removed. Let me show you guys exactly how to do that. This button you push in and pull the rod out. You just have to do it back in there behind the bezel. Now we can remove the rest of the broken nut piece. We're going to use just like a flat blade or something to pull it out. I believe it screws in there, so we'll have to unscrew it. And then we'll put our new one in. So you can see there's our broken piece. Now we just need to get our new one. Alright, here's our new switch nut. You can see it in there. There's the part number. I'll try to throw a link where I got it in the description. I got it off eBay. So all we need to do now is take our switch, put it back in there, and screw the nut in. Then we can reassemble. Now we just need to find something wide enough it can engage on both these flaps. I'm going to use snap ring pliers. You can see that fits in there on the old one. You can also use like a pry bar or anything wide enough. They don't usually make screwdrivers wide enough. That's the annoying thing. Okay, that should be good now. Hopefully. Let's go ahead and drop our dash back in place. Let's use the keys to turn on the ignition just to make sure the dash is working. Yep. RPM gauge isn't working. There we go, I think. Yeah. Alright. Oil pressure gauge is being weird. Oh, it's working. No way, it's being weird starting. Alright, let's pull those bolts out and see if there's a weird connection back here for the oil pressure gauge. We've got some kind of cruddy connection back there. And it's like a missing bolt. bad connection. I don't know what's going on there. Don't recall if it was like that before. Now let's get the trim bezel back in place. Gotta make sure to plug everything back in. And put our rod back into the switch. Okay, now let's put the fuse back into the taillight. Works. You have to get these two bolts in, the bezel. So the owner wants the Tach fixed. The reason why it's inaccurate is because there's a failed resistor network inside of the cluster. So we're going to go ahead and pull everything back apart. I'm not going to film it since I already did, and it only takes a couple minutes, so no big deal. I'll bring you guys back once I have it out on the bench, and we'll go ahead and get it fixed. Alright, we've got the cluster back out. Now we need to take the bolts, screws holding the plastic cover on. I'm going to use a 7/32 socket. I think that's 3.5 millimeter maybe, something like that. So we're just going to take all the bolts surrounding the cover on, and then it should come off. Alright, all the surrounding screws are removed. So you can see both the clear plastic cover and the black plastic surround come off. That gets us where we need to be. Here is the Tach driver board, and that's where our issue is. So let's bring this down to the bench and start looking at it. Alright, so we're here on the bench. Let's go ahead and pull our Tach driver board out, and then we can go ahead and get a look at our resistor network. It slots in down there, but obviously it has been in there for the past 20 whatever years, so it's going to be a little tough to get it out. Alright, so what we need to do is take our ohm meter and measure the resistance of this integrated resistor right there. That pin and that pin right there. The resistance spec we want to see is just under 200k ohms, although this is in circuit, so it's not going to read accurately because there's other circuit components, but we'll get a ballpark. If it's wide open, then we can just solder resistors across. If it's just incorrect, we'll cut the lead on one side, and then we'll solder the resistors on that we need. Alright, I've got one end hooked on. We'll probe. So there's our reading. We're looking at 430-ish kilo ohms, which is well above what we need. We need just about 195, I believe, is kind of what people have found is the correct value. So what we're going to do now is cut one of the legs on our integrated resistor, and then we're going to solder resistors on the back side to get the correct resistance. There you go, you can see we have an open circuit from there to there now. So we're going to go on the underside and solder some resistors in right there. So 195 ohms is not exactly a common resistor value, so I'm going to use two 100k ohm resistors in series. So there's a tolerance. If you don't know how resistor codes are read, on this one, this is a 100k ohm resistor. You have brown, black, yellow, gold. So brown black means 1 0. Yellow is the times 10, and in this case it's times 10 to the 5, I believe. And the gold is the tolerance. So gold means plus or minus 5%, if I'm remembering right. Maybe 10%, I forget. I think it's 5%. Anyways, it doesn't matter. The tolerance is fine. We don't need exact. We just need something around 195 k ohms. So we'll go ahead and measure the value of these. So this one's 103 kilo ohms. And that one's 100.6. Pretty dead on. Since I've got a ton of these 100k ohm resistors, I'm going to go through and try to find one that's just a little under 100k. That way we're not overshooting too far, but it wouldn't really be a big deal. These tachs aren't strictly accurate anyways. They're just kind of a, close enough kind of thing. Yeah, whatever. We'll just go with what we got. Let's see how it does. So, got our two resistors here. I'm going to get the soldering iron warmed up. So we need to solder these resistors in series across this terminal and this terminal. this one, and that one. So obviously these are a little big, so we're going to go chop off the excess. So I'm actually going to solder them in series like this, if it'll focus. There we go. Bending that lead back, I'm going to connect it to that one just so they're side by side, as if they were in parallel. We're just saving a little bit of space. So I think we're going to glue these together or something just to keep the vibration down, because vibration will work harden the leads and they'll get brittle and break. But for now, we'll just solder it in and test. So we're going to reflow some new solder in there. That's what that's called, because a lot of times this solder in here is just old and gross. They used some weird stuff back then. And nowadays they use lead-free, so it kind of sucks too. This is much harder to do in front of a camera than you'd expect. Or with a camera in front of you. That's the hard part. Okay. There's our series resistors. Now we should be good to test. Okay, so now is the point where you would go ahead, plug this back in, get the cluster back in the car and test it. I've got the stuff to bench test it though, so we're going to go ahead and do that, even if it's just to kind of show the theory behind how this works. But the best way is just to go plug it back into the car and test it out. But since I have the stuff to bench test it, I'm going to. So the pin out on this thing is 12 volts, ground, and then this is all for driving the Tach needle, and then this is the ignition pulse input from the distributor. So what we need to do is we need to apply 12 volts here, ground here, and we will simulate an ignition pulse here, but we need to do it obviously while it's in the cluster. So what I'm going to do is get some of those little hook grabbers and hook on 12 volts to that diode leg, ground right there, and then the ignition pulse, if we flip the board around, just comes right into this diode leg, so we'll put the ignition pulse into that. And what the diode does is it just cleans the signal up, removes any AC component. So just to make it easy on us, I'm going to put our positive lead on our little film circuit. You can see it's this plus right there. Perfect. And then on here, I'm going to connect our ignition pulse and also the ground for our ignition pulse. Let's see if we can find a ground on this board. Well, there definitely is one, but let's see. There's an exposed area. It looks like here. Now we'll go ahead and insert our board back in. And on our power supply, we're going to turn our current limit all the way down, just so in case we have something hooked up incorrectly, we're not going to fry everything. Turn it up just enough that we're on constant current. Constant voltage, I mean. There we go. Okay. Then we're going to slowly wind up the wick to 12 volts. I haven't used this thing in a while. There might be a capacitor that went bad, and I've had this happen before. Yeah, I think that's what happened. There's a big electrolytic capacitor across these two terminals. And when it goes bad, it oscillates like how I was doing just a second ago. Yeah, you see it's being all weird. But you can see it's not drawing crazy current or anything, so... Okay, not a big deal. We can switch power supplies if we need to. That one's kind of... that's really annoying. Yeah, we'll switch power supplies. Okay. You got 12 volts across it. You can see the needle gets energized. Now to our frequency generator. This is just a cheapy one, but it'll make what we need it to. So we're going to change the waveform to square wave. Pulse is fine too. Change our amplitude to 12 volts. Duty cycle, and we're going to turn that down. The frequency, we're going to start at 4 hertz, 4.7. There's a little chart show you guys in just a second. 4.17. We'll turn on our output. Misread it. I think it's 33 hertz actually. Okay, so 33.3 hertz should be 500 RPM, and we're looking pretty good. It's off a little bit. A needle's width. Not a huge deal. So now I'm going to increase it to 53.3. That should be 800 RPM. Yep, that's about right. Now 66.7 should be 1000 RPM. Dead on. There's some parallax error. Yep, dead on 1000. So now we're going to go to 100 hertz. There we go, 100 hertz. That should be 1500 RPM. Pretty close. Then we're going to go to 133 hertz. That should be 2000 RPM. Pretty much dead on. Then we'll go to 200 hertz. 3000 RPM. Next 266.7 hertz. 4000 RPM. Now we'll go 333.3 hertz. That should be 500 RPM or 5000 RPM. Dope. Perfect. Now we go 400 hertz, 6000 RPM, and then 466.7, 7000 RPM, and that is the limit of our Tach. We can go over a bit. So yeah, we're looking pretty good. So if you're curious what I was doing on the frequency generator, pretty simple, just changing the frequency. Bench is a huge mess, like every bench. You see as I turn it down, it goes down. As I turn it up, it goes up. The chart I was using is from a website, and you can see that's 0 right there. Totally off is the stop, and then 0, if you actually look at the scale, that makes sense that that's 0 right there. So anytime 12 volts is applied, it rests right there. And then as we wind up the wick on the frequency, it increases the needle displacement. So there we go. Pretty cool. Now, just because I've got one, and we can, let's fire up the oscilloscope and take a look at what the output from the signal generator actually looks like. Let's turn off the signal generator output. Let's turn off the power supply too. Pull the board back out. And all we're going to do is clip our oscilloscope lead to the same place as the function generator. We need to clip our ground to ground. Okay, there we go. Turn our power supply back on. Turn our function generator back on. Here is the oscilloscope. This is about the most bare bones oscilloscope you can get. Looks like it needs adjusted. I haven't used it in a while. Make sure, yep, shown channel A. Okay, now that you're set up so you can actually see, let's get this dialed in. There you go. The reason it's flickering is because it's a CRT, and the time base is slow enough that the screen refresh is slower than what our eyes can see. So if I turned up the time base, this looks like a solid line, but it's really not. You can see as we zoom out, increase the time base to the point that you can literally watch the dot go across. And what's funny is back in the day, how they would image very slow signals is they would actually get like photosensitive paper, like film basically, put it against this in a dark room, and it would actually leave the trace on the film. Pretty cool. Now, any cheap oscilloscope you buy has like 1,000 times functionality of this. So there's our pulse, and you can see as I increase the frequency, the distance between the square waves is going to decrease. Well, not the distance, but the size basically. The amount of square waves that fit on the screen is going to increase. The frequency is increasing, but that's about the max that the tachometer is ever going to see, because right now we're at red line, so pretty neat. Okay, well, we know it works now. Let's go put it back in the car, make sure it works in the car. That's the most important thing, right? Then I think we can call that fixed. Just in case somebody's curious for whatever reason, somebody figured out all of the correct ignition pulses for a given engine RPM displayed on the tachometer, so that's the table I was referencing. Alright, I've got the cluster back in there without the plastic lens, but that's alright. We're just testing. Okay, let's fire her up and hope that the tach works properly. Almost. Let's check for fuel pressure. I don't hear the pump priming. Hit the Schrader valve way back in there. I don't know why. Oh, it's not a Schrader valve. It's those awesome weird ones. Let me turn it on, prime it again, and let's see. Huh. Do it one more time. Yeah, nothing. I mean, obviously this is not a pressure test. We could hook up a gauge, but you saw that little spurt in the beginning when I first depressed the valve inside. Hopefully you did at least. I can see it. And after turning the key a few times, there's no pressure building up. So for some reason, the fuel pump is either donezo or not getting turned on. Huh. Well, you missed it, but I just tried again and it's working. So that's weird. Probably need to look into that because I doubt the owner wants to have to deal with that. But on some better news, the Tach is working. We're at high idle right now because it just started up. It's cold, obviously, and we're sitting at about, I don't know, a little over 1,000 RPM. Looks good to me. So I think we can button the dash up for good. Very strange about the weird starting issue, though. Let's give her a little bit of RPM. Yeah. Cool. So we have the Tach fixed. That was our big thing. I'm going to pull it back out, put the lens on. It's just the reverse of removal. Super easy. We're just going to make sure everything's plugged in and screw everything back together. So I'm going to shut her off and get it back together. Alright, now that we've got our Tach fixed, he also wants the speedometer to be accurate. And right now, like you saw on our test drive, it's off. I think it was around 5 or 7 miles an hour. So what we're going to do is look at the Speedo gear that we have in there. Probably the inaccuracy is from the wheels that we switched to. It had 16s on it before. Now it's got 17s. I don't know the overall diameter difference. So we're just going to plug all of our stuff into one of those calculators. You do tire size, rear end gear, driven Speedo gear, and drive Speedo gear. So we're going to take the speed sensor out of the output shaft of the transmission, see what driven gear we have in right now and what drive gear we have. And then we can figure out what driven gear we can switch to make it a bit accurate. Here's our speed sensor, and it looks like actually it's been leaking out the seal a little bit. You see it's all greasy and there's wetness around. So it's good that we're doing this because the seal needs replaced anyways. So it's just held in with a 10mm bolt, as you can see it through all the grease right there. And then obviously there's a wiring harness connection there. So we'll pull the bolt out, pull the speed sensor out, and then we can take a look at what gears we have in there right now. I'll bring you guys back once I have it out. Alrighty, here we go. Might have some drippage. Yeah, so I'm gonna go grab a pan to catch that. Of course, most of it already had fallen out. Okay, so we've got a white gear with the count the teeth on that, just drop it in there. And we've got a red gear on the shaft. If I'm not mistaken, that is 17 tooth. Let's grab our gear that fell into the cup and then figure out what we need to do from there. Okay, so here is our driven gear, and you can see printed right there, 44 tooth. I also went ahead and counted them. It's 44 tooth. And I was correct, the red gear, the red drive gear is 17 tooth. So just going off a chart from a Camaro forum, I believe we actually need a 43 tooth, but we'll also go through a calculator just so that we can see how that compares. So to find the correct driven gear for our Speedo, the calculator needs to know 3 things. It needs to know the tire size so that it can know the overall diameter of the wheel. We have, I forget, I think it's 245, 45, 17s on this. So we'll input that into the calculator. That'll find the diameter from the top tread to the bottom. We also need to know our axle ratio, and then it also needs to know our drive gear, which we already know. So for the axle ratio, you can either look on the tags on the axle. I already changed the oil in it, I didn't see a tag. But we know this should be at 323, just going off what the 350 automatics came with. But we can look at our RPO codes. The G codes are the axle. We've got G80, that's posi track. And then you see here we've got GU5, that's 323 axle ratio. So we have a 323 rear end, it hasn't been swapped. 323 rear end, 245, 45 17s, and a 17 tooth drive gear. Let's go get on a computer and then put that into our calculator. Okay, so here we are, we're on TCI Auto's speedometer gear calculator. We've got our drive teeth, 17, axle ratio, 323. We also have a tire diameter calculator, so we put 245 width, 45 aspect ratio, 17 diameter, and that gives us 25.7-ish tire diameter, 25.7. So driven teeth, we need 43, pretty much exactly. So we are 1 tooth over. On the same page, TCI has the 700 R4 speedometer gear color chart, so you can see red, 17 tooth. And we currently have a 44 tooth, dark gray, that matches up with what we got. So we need a 43 tooth, purple. So I will get that on order, we'll get it in and check if that brings us back into spec. Alrighty, our new Speedo gear arrived, and this thing was not easy to find. Apparently the 33 or 43 tooth is not a common part. I guess it was only used in the Corvettes in some combination of transmission and rear end, so it's not easy to find. Probably the best way to recalibrate the Speedo if you can't find the gear you need is to just do a PCM flash, but we're just going to use the gear. This should get us dead on. I was able to find it. It wasn't easy, and this was the last one I could find anywhere, and you can see it's NOS from 90, so yeah, good luck finding one of these. But anyways, let's go get this back in the car and see if the Speedo is a little bit more accurate now. It's always a good idea to grease up your gear and definitely your O-ring. So we're just going to set it back in to the housing. Make sure we plug the connector back in. Tighten up the 10mm bolt that holds it, and we'll take it out for a drive to see how it does. Yeah, it's a quart low. Alright, our speed sensor's back in. We should now have an operational Tach and an accurate speedometer, hopefully. So let's take it out and test the speedometer. Put some gas in it too. So we got our GPS speedometer, so we can compare. Those are usually pretty dang accurate. Okay, we're at 30 and it was reading 31, so it's fairly close. Let's see, we're at 40 now, 50. I think we can say that our Speedo is a lot closer now. Before it was about 5 miles an hour off, which isn't a big deal, but it's fixed now, so yeah. Alright, I think that about wraps it up on the Camaro. We got everything that needed done. We got all the fluids changed, brakes work now, they don't lock up in the middle of the road, so that's a plus. Speedo works and Tach works, so I think we can call that good. So we're going to send this down the road. Thanks for watching, guys, and I'll see you next time. When you were in bed asleep,